Okay, for this homework video, we're going to do 5, 11, and 17, as I think those encompass the different types of problems here and demonstrate the different ways of thinking about each of these problems and trying to strategize in terms of using what we've been exposed to in this lesson, which is circular permutations, permutations with repetitions, and reflective permutations with like a bracelet. So hopefully most of what is important here, as I've tried to emphasize, is the thinking aspect of it and trying to figure out how you're going to tackle the problem, which I think is a very important skill in mathematics and life in general. So looking at number 5, how many different ways arrangements can be made with 10 pieces of silverware laid in a row, and three are spoons, 4 are forks, and 3 are knives. So if we have 3 spoons, those are 3 different objects. And if we, let's say, name them spoon 1, spoon 2, spoon 3, there are 3 pick 3 or 3 factorial ways we can arrange those. Given they're different objects and it's a permutation. However, any sort of arrangements of those S1, S2, S3, or S3, S2, S1, and so on, those are all the same. So that makes this, and we can treat this like a repeated or a permutation with repetition. So first off, we're going to count up how many objects we have because we're selecting all of them. We're picking all of them, which means permutation. We have 10 pieces altogether. So if we select all 10 of them, it would be 10 factorial, which is the same as 10 pick 10. And then we're going to divide it by the factorial of the numbers of forks, spoons, and knives. So first off, if there are 3 spoons, we are going to divide by 3 factorial because of the reason I talked about in terms of S1, S2, S3, and the rearranging of the orders of those gives you the same possibility. If there are 4 forks, we need a 4 factorial in the denominator, and 3 knives, we need a 3 factorial. And that will give you some number, which you can easily calculate. This doesn't seem like too difficult of a problem. The goal is to try to recognize this, because when we kind of pull back and we look at all the different counting methods that we have throughout the whole unit, and you get thrown a problem like this, that thinking of being able to determine that's a permutation or repetitive permutation makes the problem much easier to tackle. Okay, moving on to number 11. How many ways can 8 charms be arranged on a bracelet which has no clasp? So if I think of a bracelet and it has no clasp, that's saying that there is no marker on it, just like sitting people at a round table, there's no marker in the room, so therefore it is going to be a circular permutation. So because there's 8 charms and it's a circular permutation, that part of it's going to be 7 factorial, which, if you recall, circular permutation is n minus 1 factorial. So if there's 8 charms, the different, because of the circular nature of it, there is going to be 7 factorial. And this again is, let's see, first we are doing which has no clasp. So again, that's what makes it circular, but it's also reflective because we can look at the bracelet from one side or flip it over and look on it from the other. So with reflective, that divides it by 2. So that would be your answer if there is no clasp. If there is a clasp, so this is without a clasp. And then you can easily calculate what that is. The answer is in the solution. The solution worksheet that you were given. So with a clasp now makes the permutation not circular but linear, because now the position, if we rotated them, does matter. Because if we have, like, let's say we have a bracelet like this, and here's the clasp on it, and let's say this is a position of one of the charms, this is the position of the other, and of course we have 8 more, however many. Let's say charm A goes there, and charm B goes there, and C goes there, and so on. If we then rotated it to make A right here and B right here, that's a different configuration, because when A is here relative to the clasp, it's quote unquote above it, but here it's below it. So that marker makes it a linear permutation, and therefore we simply treat it as 8 pick 8 or 8 factorial. It's still reflective because it's a bracelet that we can look at from both sides. So with it would be 8 factorial divided by 2. Okay, so for the last ones, we have 3 men and 3 women are seated in a row containing 6 chairs. Find the different ways they can be arranged. Now, this may come into mind, like if we have 3 men, person A, B, and C, and then 3 women, D, E, and F. We are seeing that, hopefully you see that it's not repetition, because if I see person A, B, C, and then I rearrange the order C, B, A, that is actually different. Like, we can't, for the most part, determine the difference between spoons or forks or the letters, like the word T, T-E-E, E1 and E2. That ends up giving us the same letters, or the same word if we rearrange the E's in the word T. But if we're rearranging people in a line, for instance, it would be a different configuration, meaning if we took a picture and we lined them up as ABC versus CBA, that is different because there's obviously a noticeable significant difference between 2 people versus 2 spoons or letters. So all that being said, I highly suggest that you draw a sample space for this, because we have this very specific, more complicated situation of alternating men and women. So now that we have this configuration, I guess configuration would be a better word than sample space, let's come up with a situation that we have here. Let's go woman, then man, woman, man, woman, man. They need to be seated alternately. And I look at that and I go, for the women, that would be, and I'm just doing that configuration. We'll come up with other configurations. Let's first try figuring out how many possibilities we have in this situation. So for the women, that would be 3 women in 3 slots, and the order matters because they're different people. So like if I placed them woman 1, woman 2, woman 3, and those 3 slots moving from left to right, that's a different possibility than women, like women 3, women 2, woman 1. So the order matters. So for the women sitting down, it'd be 3 factorial. And for each position of the women, we have each position of the man, and therefore that's each indicates multiplication. And all the different ways that we could arrange the men would be 3 factorial. So we're going to take 3 factorial times 3 factorial, because for each slot of the women, the 3 factorial, we have each of the configurations of the men, and therefore we multiply them. However, that's only when the woman comes first and then the man. We could also have the possibility of the man being seated first, then the woman, man, woman, and woman, which is also 3 factorial, 3 factorial. These two are independent events of each other. So therefore, it's going to be that 3 factorial times 2, because it's happening twice, which is 6 times 6 is 36, times 2 is 72. And again, it's important that you can calculate the number at the end, but really the important part of this is setting it up, getting the correct counting method, rather than the ending answer at the end.